Yes, my screen visible.
Yes, ma'am.
Okay. So So now we have a three mapping techniques. Means what? From we have a main memory size very large when compared to the cache, but it would how many blocks has to be placed in a line. So we have a mapping technique. Which one? First one is a direct mapping, and next is fully associative mapping, and next is a set associative mapping. So this is about a direct mapping technique. So in a direct mapping technique. So this is a diagram, but let me explain some more examples, then I will explain this. But according to the morning class, I said that a cache, if it wants to search in the cache, will be divided into three partitions if it is direct mapping. What are those three? One is offset, block offset, which is it is mentioned here as a word, and next is how many cache lines are present. Then next is the tag. So can anyone tell me what is the use of tag? What is the use of tag?
which decides the which block in which block to be activated in
Yes,
the line.
yes. So in the line, as the size is cache size is less, so in a single line we'll be having many blocks mapped. So only one block will be activated. So that will be decided by the tag. And so this is the formula that will be decided. So which block? This is your block one. So this is your single block like that. Why it is 4 means we have considered the size of the block as a 4 words. So we have combined 4 words and make it as a single block. Okay. So in this, see here, this is very important formula for deciding which block to be placed in which particular line in the cache. So here, this is I equals to j modulo m. Okay. So what is I is a cache line number. So in which particular cache line we need to place this main memory block. So j is what? J is a main memory block number. So if you are considering block 0, so we need to place as 0 main memory block number. M is the number of lines in the cache. Number of lines in the cache. So M is the number of lines in the cache. For our example that we consider, the cache lines are 4. So M is equals to 4 and J equals to main memory block number, and it varies from block number 0 to 7. Why? Because we have totally main memory blocks 8 blocks. So as we are starting from 0, so the J value will be from 0 to 7 as we have 8 blocks totally. And cache line number means based on substituting this value, what number we are getting, that is nothing but this I value. So let me show with an example. See here. Okay. So M is the number of lines in the cache. M is the number of lines in the cache. So I is based on I. If it is showing as 0, we need to place the block J value which is selected in I. Okay. So here the formula is I equals to J modulo M. M is the number of lines in the cache. In this example, what example that I consider is the example that we considered in the morning session. So this is the example where we have considered main memory as 32 words, cache memory as 16 words, and block size equals to 4 words. Okay. So based on this, if you fragment the main memory divided by 4, you will be getting 8 blocks, and cache you will be getting 4 lines. And which block to be mapped to which, this will be decided. Based on this, we will be deciding. Okay. So now let me start with the first. Let me go for block 0. So if you take 0 mod 0, why I'm considering 0 is J is here, which block number you are selecting. So I'm considering block 0 mod modulo, and M here is the number of lines in the cache. Here we have 4. So what will be getting the value of 0 modulo 4? You will be getting the value as 0. So that indicates I is 0 is what? Here I means this block has to be mapped to line number 0. This block 0 has to be mapped to line number 0. Okay. Next is what? Next block 0 is completed. Next we'll be going for block 1. So 1 mod 4. You will be getting what?
1 month.
1. That indicates what? The block 1 from main memory will has to place in which line? In catchy line number 1. So that's the reason block 0 is placed in this block 1, which is in the main memory, has to be placed in line number 1. So if you go for the second block, mod 4, you will be getting 2. That indicates that block 2 has to be placed in line number 2. Similarly, 3 mod, you will be getting the block 3 has to be placed in line number 3. So similarly, based on this formula, I have written this. So if you substitute, you will be getting as B0, B1, B2, B3 and B4. So can anyone tell me why it is written as B4 in line number 0? Why not in some other lines? Because B0 is B4 is 4 block 4 in the main memory modulo, and the number of lines in the cache equals to 4. So the result that you are getting is 4 modulo 4. You are getting the result as
0
module 0. That indicates this block 4 has to be placed in, has to be mapped in line number 0. So if you substitute that all one by one, as here we have only 8 blocks, so based on that you will be getting the result. So in this way it is fixed, but you have to notice that amount 2 in this block, in this line, based on the memory size, it is mapping 2 blocks, but at a time it cannot be currently any one will be active. So which one is currently available in that cache line will be decided based on a tag bit. So how many tag bits are needed here? Is it 1 or 0? 2. 1 tag bit or 2 tag bits are needed according to this example. In the morning session also I asked. Okay, so according to this mapping, it is showing that in a single line 2 blocks can be mapped. Okay, 2 blocks can be mapped according to the main memory size. So among this, any one will be active. So either block 0 will be active or either block 4 is active. Processor is asking block 0. It knows that it will be available in line number 0. So it checks in the line number 0, but processor require block 4, but block 0 is available here. Then it's like a catching miss. So it has to go there and it has to replace that whatever it is available here, and whatever the processor is required, that has to be placed here. Okay. So for that, it has to know, after going to the line number, processor knows that that particular word is available in the line number 0. So if a processor wants any word from this block, so block 0 or block 4, it knows that it will be available in the line number 0. So it goes to that line number 0, then it checks with the tag. So there will be two tags assigned, one is 0 and one is 1. Okay. So as we have 2 blocks here, 1 bit is enough for showing whether which one is active. So if it is 0, that indicates B0 is active. If it is 1, that indicates B4 is active. Now let us consider if I increase the main memory size, then the cache size I am keeping as it is. And one more example also while leaving I have given. What is that example? Main memory size, how much I have given? The main memory size I have given as 64 words, and cache I have given same as 16 words, and block size 4 words. So in that case, how many blocks we got, ma? We got how many blocks? Number of blocks, if it is 64. Number of blocks, if it is
16.
16. So if it is 16, in a single line, how many will be mapped, ma? If it is 16, in a single cache line, 4. Okay. So for this 4, is that 1 bit is enough? No,
Two bits, ma'am.
we need to take 2 bits. So that indicates 00, 01, 10, 11. If it is 00, block 0 will be active. If it is 01, block 4 will be active. If it is 108, you will be getting 8. Next, if it is 11, you will be getting 12. Block 12 according to this formula. Okay. So as we have 2, so 1 bit tag is enough. So if it is 0, that indicates B0 is active. If it is 1, that indicates B4 is active. In that B4 also again, what are the words that are present is 16, 17, 18, 19. These are the words that are present. Now, for sake of understanding, let us consider processor is asking one word. So, see here, this is the word the processor is asking. So, what we will be doing? So, this is a word. So, according to your knowledge, so we have 32 words. So, morning also we discussed means physical address total will be 5 bits. So in this 5 bits, if it is checking in the cache, we'll be having 3 partitions. One is a block offset or word, and the other one is cache line number, and the other one is tag. So according to this example, tell me, 4 words means how many bits will be occupied for block offset? 2 bits. And number of lines, cache lines, we have 4, so 2 by 2, so 2 bits, and the tag bits is 1. So if you add, you'll be getting 5. Now in this case, so first, what if it is a direct mapping, this is the processor. The processor wants to search first in the cache. So what processor will do is first it directly goes to line number 1. Okay. So based on this bits, so these bits which are mentioned in this is the bits. Okay. So this has to be partitioned first. This is a word that the processor wants to execute. First, this is the processor address. Now this has to be partitioned according to the cache. So if you partition, 2 bits is for word and the 2 bits is for cache line number, 1 bit is for tag. So directly it goes to line number. First, what it will do is it knows that this word will be available in line number 1. 01 indicates it is 1. So it goes to line number 1. So here line number 1. So in this line number 1, it checks with tag. If it is 0, that indicates the corresponding word is available. So see here, if it is 0, so it is going to line number 0 and this is your tag. So it is checking with the tag. So this is a tag which is available in the processor. This is the tag which is available in the cache. So this tag and this tag will be matched. This both will be compared. If there is a match, then it is called catching hit. Then it is called a catching hit. So that indicates here tag is 0, here also 0. That indicates it is hit. If it is hit, I already said that whenever there is a catching hit, it will be word transfer, not the block transfer. So you should know even if this block is removed and placed in this cache memory means I should not say as removed, the copy will it's like a copy. So whenever you are doing in an Excel or Word, when you copy, the copy in the main memory will be existing and the same copy will be available in the cache also in the same way. So you have copied and you have placed in the cache line called B4 means what? Inside this B4 we have these 4 words. So you should know that. So it is a hit. And after hit, which word in this block the processor is requiring is based on this word offset. So it is 10. That indicates what is present in this is B1. So this is your B1. Okay. Now in this 4, it has to be placed with 0, 0, 0, 1, 1, 0, 1, 1. Means this word the processor is asking. Means what? If there is a hit in this also we'll be having 4 words. In this also we'll be having 4 words based on the position bits which is mentioned here. It is mentioned as 10. So which is word 6 will be fetched from this and will be accessed. So according to this, if you group also, it is asking 110 indicates it is 6. Here also we got a 6. So in this way, we'll be accessing the cache. Now let us suppose. Can anyone tell me why I have written here B4? See here, if you see, we have two combinations. Two can be mapped in this line number 0. Okay, B0, B4. If the tag bit represents 0, that indicates the B0 is present in this. If the tag bit represents 1, that indicates B4 is present. So in this case, the tag bit is representing as 1, that indicates internally the block B4 is present. Okay. Now let us consider, in this case, the processor is requesting this the same one. Instead of this, I will replace this one. This one. Instead of 0, I will be placing as 1. Previously it was 0, now I am placing 1. So if I am placing 1 means inside which block is available? Please answer. Inside which block is available? If I am placing 1 means,
B5, ma'am.
yes, it is B5 is available. Okay. So as B5 is available, now this is the processor address, this is the cache. Okay. So now it goes to line number 1. With 01 indicates line number 1. Directly it goes, it will not check all the lines as it is direct mapping. It goes to directly the line number 1. And after going to line number 1, it checks the tag. So the tag in the processor we have a 0, but in this case we have a 1. That indicates it is cache miss. So when it is a cache miss, then wherever the block is present, called this block, what is this block? So this is available in this one is available in block 1. So this block 1 has to be placed. This block 1 has to be placed. Now, if it is cache miss, just a minute. Yes, ma'am. Okay. So in this case, if it is this will be considered. It goes to line number 0, and after going, it checks with the tag. If there is no tag matching with the tag, that indicates that it is catching miss. So what it will be doing is whatever the block that it is miss, so it goes to that block, and B1 will be this block has to be placed instead of this B5 has to be removed, and this B1 has to be placed in line number 1. Why? Because it is fixed that whenever in a line, so it is in this line we have to fix from a block B, block 1 and block 5. No other block has to be placed. The drawback in this is that, let us consider, we are fixed. As we are fixed, some blocks are not used at all. Okay. So in such case, if there is a cache miss, we cannot utilize those blocks even those are not used. That is a drawback in a direct mapping technique. So in this case, as there is a miss in this, so it takes that block 1, and this has to be first, this block 5 has to be removed, and this block 1 has to be placed in this. In such case, even the other inside the caches, the other blocks which are not used at all will not be used. In this case, the drawback is cache miss rates will be more. Why? Now let us consider the processor is executing. A processor is frequently asking B0 and B4, okay? So, or B1 and B5. Till now we have discussed about B1 and B5. No? So, we removed B5 and we placed B1 here, and we removed that the tag as 0. Why? Because according to this, the B1 is present here. Now, I removed B5 and I placed B1. After this, next if it is asking B5 again. So even the other lines words we are not using at all. We are frequently removing and we are placing as it is fixed. Why? Because this block has to be placed in this particular line only. So the number of cache miss rate increases. Cache miss rate increases. If there is a miss again, If a processor require block 5 but this is not available, block 1 is available in this line, it considers again a cache miss. Again it goes to the main memory and whatever the block is there, it will be placed in that line. Again a processor require B1, next B5, B1, B5 like that. In this case as it is 2, but in reality it will be more. If in the same line, if it is asking the same different blocks in that line, that indicates caching miss increases. So to overcome that, we went for one more mapping technique called associative mapping technique. Okay, we went for one more technique called associative mapping technique. But let me explain with the diagram. Here is this one. So this is your direct mapping cache organization. This diagram is very important one. So you must understand this very clearly. So see here, this, let us consider this is your memory address. Okay, so which is given by the processor. So will be divided into three partitions if it is direct mapping called a tag, line, and a word. Word is represented by W, line is R, and the remaining is S minus R. Okay, which is tag. Okay, so what is this? Can anyone tell me the main memory partition? You will be having two only. What are those two? One is W, which
Block
is in,
offset and
and block number.
block number.
Yes, block number here in this case it is represented as S. Okay, so as we have only two, it is given as S plus W. S plus W. If you add, you will be getting a physical address. So in our example, W is 2 and S is 3. If you add 5 bits, 5 bits is a physical address. So this is our 5 bits. So if it how to identify whether it is a hit or a miss? First, it goes to particular line number. Why? Because processor knows that it is available in this particular line. So it goes to that particular line. Next is it checks the tag bits. The tag bits which are present here, which is given by the processor, and the tag bits which are present in the cache, and the tag bits which are present in the cache. This both will be compared. If both are same, then we'll be representing this as a hit in cache. Then we'll be representing this as a hit in cache. If not, it is missing cache. So what we need to do if there is a miss means we need to go to this main memory and we need to whatever the block the processor is require, we need to replace that and we need to place. This is about if comparison is okay, then if it is matched, then it is called hitting catching. If it is not matching, then it is called a missing catching. So if it is missing catching, it has to go to main memory and it has to check with those words and the S which it wants. S is what? The block number. So it goes to that particular block number which is S. So if you remove this tag and line, this will become a block number. So it goes to that block number. Goes to that block number and what example that we have considered now 00110. Is this example that we have considered processor 5 bits? Yes.
Yes, ma'am.
Okay, if this is an example that we have considered, if it is miss, then this will be divided into two partitions. So this is your block number, this is your offset. So it has to go to block B1 for getting this word 6. Is that okay? So see here. So it requires word 6. So in order, if there is a miss, then in main memory, to which block it has to go for getting this word is. So it has to go to block 1. It has to go to block 1 based on the example mentioned. And in that, as it is 10, 0, 0, 0, and 10, this one. This is your 6. So in this way, if it is miss, then you will be converting to two partitions. If it is hit, you will be having three partitions. So in this way, where is this? Okay. So in this way, if you have a first, In the direct mapping, it goes directly to a particular line and then it checks with the tag. And if the tag is matching, then it is said to be catchy hit if there is no after comparison. And if it is not matching, then it is said to be catchy miss. In such case, we need to combine this tag and line to find out the block number. So in such case, S will be indicating as the block number. So you will be going to that particular block, and W is what? Inside that, if two bits are used for a block offset, if it is representing as 01, so it goes for 0001, and this is the block the processor is requiring. This is the block the processor is requiring. So it places and it removes any one of the cache. And one more question I want to ask, but let me complete here. See, if there is a hit, then what happens when now the tag which is present here and the tag which is present here is compared and it is hit. Next is what we need to find out the word. So which word? Why? Because the processor is not uh, not needed all the words. It is requiring only a single word in this. We have four words. So which word it has to be sent is based on the offset number. So if it is mentioned here as 01, so 0001, this word has to be given to the processor for execution. Now, do we require replacement algorithms? So we have studied about in this when there is a catching miss, what we are doing what? When there is a catching miss, we are going to main memory and whatever the block that is available in the main memory, we are placing in the cache. For that, we need to remove any one of the cache line based on the replacement algorithms, right? Like least frequently used, least recently used, first in, first out. Do we require this type of an algorithms in direct mapping? Are they required in direct mapping? Answer more fast. I getting my point first of all. See here. What question I asked, Emma? The question that I asked is, let me show with an example, then you can understand. See here, this is your CPU and this is your cache and this is your main memory. Okay, so which blocks has to be placed in which particular line, that is like a direct mapping. But I'm asking if it is a catchy miss, that indicates the processor whatever it is asking is not available in the cache, it is available in the main memory. For that, what we need to do, whatever the processor is requesting, this has to be placed in the cache. But anyhow, this will be filled with all the blocks in the cache. Why? Because the size of the cache is very less. So in such case, what we'll be doing? Can we remove any one of the lines randomly? How to remove?
No, ma'am, we cannot remove like that.
How to remove based on a replacement algorithms. So last class also we had discussed. So least recently used, least frequently used, first in, first out. And so among all frequently used instructions, which one is not used instruction, that will be removed. So if you are not using all those concepts, simply if you remove whatever the block that is available in the line to will be removing it. Next time, frequently that the same what we removed will be asked by the processor. To overcome that, we need to apply some type of a technique so that if you remove, that will not maximum of the time that whatever that we remove to place the main memory content inside this, the processor should not ask that frequently. Okay, so we will be applying some sort of algorithm technique so that from maximum of the time or from one day, it is not asking that. So we'll be removing that. So is it needed those type of a techniques in direct mapping? I'm asking. Is it needed? అవసరమా మనకి రీప్లేస్మెంట్ ఆల్గరిథమ్స్ డైరెక్ట్ మ్యాపింగ్ లో? Direct mapping and ఏంటమ్మా in
No,
a
ma'am.
line. Then how much time you are taking? That indicates that no one is. It is up to you, ma'am. So in a direct mapping, we don't. It will not support that. Why? Because if there is line zero, if a processor goes to line 0 and if there is a catchy miss, that indicates the missed block has to place in line 0 only. Even you have an empty slot, it is not supposed to use that as because it is mapped directly. These blocks has to be mapped in these lines. So if there is any miss, we cannot use some type of a technique algorithms based on that. After using an algorithm, it identified that this is a line in this block which is not using from the maximum of the time. We can remove this so that the frequently used instruction can be placed here. Such type of algorithms will not work for a direct mapping. Why? Because it is fixed. Even it is fixed. So we should know if whatever the block which is missed, that has to be placed in that line only. We cannot apply any type of algorithms in this for making efficient. That is one problem in CP, in a direct mapping, in a catchy organization. అర్థమైందమ్మా? Please answer me. Or
Yes,
else I
ma'am.
will.
Yes, ma'am.
Others. Direct mapping, in a direct mapping techniques, we will not be using any type of algorithms for removing any one line in the catchy. Why? Because without applying any type of an algorithm, if you remove the next time, it may add the same one which we removed recently. So we'll be applying some type of an algorithm that cannot be applied in a direct mapping. Why? Because we know that this block is fixed in line number. So that line number only, the present block has to be removed and the block which is requesting by the processor has to be placed. So that is about direct mapping. Yes, ma'am. Now you're done. Tell me the advantages of this. So this is about S plus W that we discussed. This is your total address length. So 2 bits is for offset. For the example that we considered, S is the 3 bits. So 5 bits is the address length, physical address length. So main memory blocks how to get. So this total 5 bits divided by the word, so that you'll be getting this will be discussed in this only. Now, can anyone tell me the advantages fast? See here. The advantages, it is easy. So it will it is not needed to search each and every line to find the block in the catchy. So just now I said no. Replacement is a straightforward. So we are not using any replacement algorithms like LRU, LFU, FIFO, FIFO, all those. So it is very easy. So the disadvantages, many blocks in main memory are mapped to the same catchy block, and even we have any type of an empty slots in the catchy, we are not utilizing it. So utilize poor catchy utilization. And one more is, it is not mentioned here. Can anyone, just now I said, what is the drawback, main drawback in direct mapping? Catchy miss rate increases. Can anyone tell me when catchy miss rate increases? When a catchy miss rate increases? In which scenario?
Because
Yes, because
as there are empty slots in catchy memory, there is a need in catchy miss, ma'am. Because only particular line can hold only a particular block, respective blocks.
yes. So because of that, catchy miss rate increases because in a single line, let us consider, according to our example, we mapped only 2 blocks. But if the catchy size is small and main memory size is large, in such case, in a single line, we need to accommodate so many blocks, like based on our example, like 4, block 8, block 12, like that. So let us consider single line, we have 4 blocks. And frequently if a processor is asking one by one, block 0, next block 2, next block 8, next block 3. Are we using any other lines in the cache, or only same line we are using frequently?
Same line, ma'am.
That's the reason. So when it is asking B0, then B1, then B2, that indicates them all are like miss. So initially, if processor is asking B0, but initially it is B2, then we need to remove B2. We need to place B0. Next, we remove B2. Next, it is asking B2. Again, we need to remove B0 and we need to place B2. Then cache miss increases because of this direct mapping. But advantages, it is easy, and if we have a number of lines, we are going to only particular line. So I will stop the direct mapping. So let me take one more example, then I will stop. So till now I have discussed only like a words in this way, but in reality you will be like GBs, KBs. So in such case, so how to? So let me take with an example, then you can understand. So it was okay. Okay, let me take this. I will end just a minute. Note down in your notes who answers first, they can leave. So cache memory size equals to 2K. Okay, and main memory equals to 64 KB, 2 KB, 64 KB. Okay, am I audible, ma'am?
Yes, ma'am.
Okay, okay. And I want to do fragmentation, 16 words per block. 16 words per block. Okay. First, before going to this, tell me the physical address bits. Anyone I will see who will do. Physical address. Physical address. And before going for this physical address, you must be very clear about KB, MB, GB, TB, PB, all those. Okay. So we have discussed about the second unit in 8086 architecture. We have a memory of 1 MB, which is equals to how much more? 2 power? We have discussed in 8086 architecture where 8086 will support 1 MB of memory, which is of 2 power?
9, ma'am.
Okay, I will see for 2 minutes. Anyone will answer physical address.
2 power 10.
Yes, see here. It will be confusing in the initially, but let me explain. KB is nothing but 1 KB is nothing but 2 power 10. Okay, so our memory size is 1 MB in 8086. Our address bits were 10 address bits or 20 address bits. 8086 will support how many address bits? 20 or 12 or 10? So MB 1 MB equals to 2 power 20. And next is what? 1 GB equals to chapter number 1 GB equals to 2 power GD. 1 TB equals to 2 bar 40. 1 petabyte. P equals to 2 bar 50. Okay. So now, how much is this cache memory? But I'm asking you the first question is physical address. Physical address means will you go for main memory or will you go for cache memory? Physical address is calculated by main memory or cache memory?
Main memory.
Yes. So main memory is of size 64 KB. So 64 KB, I can write this as 1 KB into 64. 1 KB is 2 par. How much is 1 KB? 2 par?
About 10 more.
10 into 64 means how much? 2 par? 66. So which is equals to 2 par 16.
60.
Means we need physical address. How many bits?
16 bits.
16 bits. Okay. But we have still not fragmented. We have not fragmented. This is your actual physical address. Whereas in the previous case, we have given 32 words. So we got the physical address as 5 bits. In the 5 bits, again, we have to divide according to the main memory as two divisions. What are those two? One is a block offset and the other one is block number. Okay. So for that, let me clear this. So till now we have this how much I have given 2K, main memory as 64K, and how many words, ma'am? 60 words.
16, ma'am.
Okay. So now we are done with the physical address. So physical address is, we know it is 16 bits because the main memory size is 64K. Okay, done. Now tell me how much is a block offset? We have 16. Means how many bits are occupied for that? 16 means 2 power 4.
4, ma'am.
So 4 bits for block offset. And remaining will be block number. So how to identify how many blocks will be present in the 64? Now I want an answer first. So 2 power 16 divided by 2 power 4. Okay, na? So we need to divide that entire main memory 64K, and in each slot I want 16. So 16 is represent 64K. I'm represented by 2 power 16. So this I have to represent it by 2 power 4.
4.
How many bits you will be getting? 2 power 16 minus 4. 2 power
12,
2
ma'am.
power 12.
12.
2 power 12. That indicates 12 bits are required for representing block number. Okay. Now 2 power 12 equals to how much? Tell me. Like I want how many blocks we require if it is main memory size is 64K. Can you block some 2 power 12 and
4096, ma'am.
Yes. So it is 4096. When this type of questions if they ask, you need to represent that we have a main memory. This is our main memory with 0 block 1, 2, 3 until 4095. You have to show this with this example. Now we got this is for main memory. Then now we'll be going for cache memory. So for cache memory, how many partitions we'll be having? 3 or 2 partitions? 3. So let me start with cache memory. Again, if I remember. So again, I have to get 2K, main memory 64K, and 16 words in each block. Now tell me. So cache, it is, you know that it is 16. But the 16, if it is main memory, will be divided 2. But if it is cache, will be divided into 3. What are those 3? One is same. Here, this will be same. So how many bits you will be getting?
4, ma'am.
4. This is cache line number. So this you must do. catchy line number. How many lines in the catchy? So 2k means how many bits to power? How much is 2k? 2k is represented as 1k into
1K, ma'am.
1 into 2, you will be getting 2k. Okay, so 1k is represented by 2 power, how much is 10 into 2 power
11.
2 power 1. So which is equals to 2 power 11 by 2 power. Again, this catchy is the whole it is given. Still, we have not fragmented. So the given is 4k divided by 16 words means how many lines are you getting? One divided by 16 and 2 power 4.
4.
You will be getting how much? 11 minus 4 2 power
7, ma'am.
7.
Yes. Means for catchy line numbers it is 7. Now tell me 2 power 7 equals to how many? 2 power 7 equals to, is it 512 or is it 128?
128.
Yes, it is 128. So you have 128 catchy line numbers and you have 4096 blocks numbers based on this partition and tag. Tag ela cheptarama. So blocks divided by catchy line numbers, you will be getting a block. So how many blocks we have in the main memory? 4096 divided by how many lines we have in the catchy? Lines in the catchy?
128, ma'am.
128. So how much you are getting? 4096 divided by 128 ఎంత వస్తుంది?
32, ma'am.
32
5
means
bits, ma'am.
okay. So it is 32. అంటే ఎన్ని బిట్స్ రావాలి ట్యాగ్ బిట్స్ కి? 2 power
5, ma'am.
2 power 5.
5.
5 bits. If you add, you need to get 16. Osmaya, 7 plus 4 plus 5. Are you getting 16?
Yes, ma'am.
Yes,
So
ma'am.
in this way, we need to do the bits. So in the exam, they will be asking catchy, given a catchy size, given a main memory size, they will be giving a fragmentation size. Then calculate the number of tags and lines and bits. For that, we need to start with calculating the physical address. Then go for main memory, then go for catching. Is it clear, ma'am?
Yes, ma'am.
Yes, ma'am.
Okay, then I will stop.